Hello friends, today we will discuss reaction kinetics with the help of potential energy diagrams. We all knew that T is a notation of total energy, P for potential energy and Ke for kinetic energy. So basically total energy is the summation of potential energy and kinetic energy. Here is the graphical representation of energies. Uh, this curve represents the white line is the total energy, the yellow line is the kinetic energy, and the pale red color is for potential energy. So now we see the white line is straight, so that means total energy is constant. If the case is like that, then if kinetic energy increases, then potential energy decreases, and in the same manner, if kinetic energy decreases, then potential energy increases to maintain the total energy as constant. There are two types of reactions. One is exothermic reaction and the second one is endothermic reaction. The name itself explains exothermic means loss of heat and endothermic means gain of heat, or we can say consumption of heat. This is the same representation in the tabular format for exothermic reaction and endothermic reaction. The new parameter is change in enthalpy. For exothermic reaction, the change in enthalpy is negative, and for endothermic reaction, the change in enthalpy is positive. Here are the definitions. Like for kinetic energy is defined as heat energy due to particle motion, and potential energy defined as heat energy due to position of particles. These are the formulas. For kinetic energy is well-known formula like half mv square, where m is the mass of the particle and v is velocity of the particle moving. Now we will discuss heat of reaction is denoted by delta H, means the change in enthalpy. The delta H is equal to the enthalpy of product minus enthalpy of reactants. So the delta H is this change in enthalpy. If enthalpy of product is greater than the enthalpy of reactant, then the reaction is exothermic. And if the enthalpy of product is less than enthalpy of reactant, then the reaction is endothermic. Now we will discuss exothermic reactions. Consider the simple reaction like A2 reacts with B2 and gives a product AB. So it also gives the reaction energy 100 kilojoule. These reactions are represented by two ways. One is this one and second one is this one. Both are correct and same. So if delta H is negative, that means it releases the energy. So it releases the heat in the environment. So the reaction is exothermic. Now how the reaction happens? There are four stages of reaction. One is approaching of two reactants towards each other, then collision, then third is bond formation, and fourth one is product formation. Now in this first graph, we see the x-axis is denoted as potential energy. So the two reactants are coming towards each other and they collide, and there is formation of complex, and after that the product formation will occur. Now let's find out the energy of activation and change in enthalpy or heat of reaction. Suppose A2 reacts with B2 giving us the product twice AB, 2AB, and release of energy which is 100 kilojoule. So the energy of activation is as represented in the graph is this one. This is the energy of activation, and change in enthalpy or heat of reaction is this one, delta H. From the graph we can also find out the energy of activation, but for a reverse direction of reaction. So this is the energy of activation in reverse order. Now consider the example for exothermic reaction. Given that enthalpy for reactant is 400 kilojoule and energy of activation is 200 kilojoule, and also the change in enthalpy, that is heat of reaction, is minus 100 kilojoule. So we need to draw the potential energy diagram. So on x-axis we plot the energy, and on y-axis we plot the. Now here we consider the example for exothermic reaction. We have enthalpy for reactant is 400 kilojoule, energy of activation is 200 kilojoule, and change in enthalpy, that is heat of reaction, is minus 100 kilojoule. So how to draw a potential energy diagram from the given data? So now we know that change in enthalpy or heat of reaction is equals to enthalpy of product minus enthalpy of reactant. So putting this value in the equation, we calculate enthalpy of the product, which is 300. So we have all the data, and from that we can draw the graph. So we calculate the enthalpy of product. So we have enthalpy for the reactant is 400, that is this, and energy of activation is 200. So 400 plus 200 is the 600. So energy of activation is comes in the range of this 600, and as we calculate enthalpy for product is 300. So this is the graph for our potential energy diagram. Now let's consider the endothermic reactions. Considering the reaction A2 plus B2 plus 100 kilojoule giving the product AB. So this is also represented by two ways, and both ways are correct. Here delta H is plus 100. That means it consumes energy. So that's why it is endothermic reaction. Now consider the example for endothermic reaction, and we have the following data, like enthalpy for reactant is 400 kilojoule, energy of activation is 200 kilojoule, and change in enthalpy is plus 100 kilojoule. So from that we need to draw potential energy diagram. As we did previously, we similarly calculate the enthalpy for the product. We're putting the values in the equation. Delta H equals to enthalpy of product minus enthalpy of reactants, we are getting the enthalpy of product is 500 kilojoule. And now it's easy to draw the potential energy diagram. So on y-axis we have energy, as from the data we know the enthalpy of product is 400, energy of activation is 200, so 400 plus 200 is 600. And as we calculate from the formula, we have enthalpy for the product is 500. So this is our graph looks like. Thank you friends for listening.